So hi everyone, welcome to the next class of your chemical engineering thermodynamics. So as we all know from the last class, right, हमने first law of thermodynamics cover कर लिया है, right? So with the problems in closed system, open system, everything is done. ठीक है? So I told you almost 75% is over. This is the last 25%. ठीक है? So this is our next chapter called second law of thermodynamics. So what is the meaning, right? What is the meaning of second law? Why we need a second law? Because the first law is not adequate, right? Or we can say what, right? With first law we are not able to explain the things fully, right? That's why we need a second law, right? Right? So there will be some problem with the first law. The first law is not enough to prove something, so that's why we have a second law. Okay? Same thing, yeah, right? So if you are having a cricket, right? So in cricket we are having what? Minimum 30-40 rules are there, right? Then only we are able to cover the entire ground, right? Or entire game. Same way, right? We need what? We need second law. Then only we can at least be sure of about a process. Right? So a process will happen, right? A process will happen only if it satisfies both first and second law, right? So if it is not satisfying second law, the process will not happen, right? So that is the meaning. So it should satisfy both first law and second law. Clear? I hope you understood. 1 minute, let me check. I hope the board is visible. So there is some clear. So there is some focus issue. Let me check 1 minute. So I was saying, right? So what I was saying is a process cannot take place unless it satisfies both your first law and your second law. Okay? And the problem is every process happens in, right? Every process happens in only a particular direction. It may not happen in the same reverse direction. So your first law, right? The problem with first law is not giving any restriction to a particular process, right? It is not against any particular process. For example, it is not giving any restriction to a particular process. You can see here. What is the meaning of first law? मेरे पास एक 70 degree Celsius container है, right? Your surrounding is at 30. So 70 to 30, there will be a heat transfer. Right, so it is a heat transfer process, right? So from 70 to 30, there is a heat transfer process. Now, what is the problem actually, right? What is the problem? So 70 to 30, there is a heat transfer process. So according to your first law, what is the meaning of first law? Heat lost by the hot system is equal to heat gained by the cold. Clear? यही तो first law है अपना, right? 70, whatever heat lost by this particular system is equal to whatever heat gained by the surrounding. Heat lost is equal to heat gain. यही आपका first law है, right? Now if I say there is a heat transfer in the opposite direction. Imagine, right? You can imagine like this. ठीक है? Imagine कर लो. Now if you have a heat transfer process in the opposite direction and I am saying, right, heat gained by the system, right? If I say heat gained by the system is equal to heat lost by the surrounding, is it correct? According to first law, this also satisfies the first law, no? Right? Energy can neither be created nor be destroyed. Same thing, right? That is, this is your surrounding. 30 degrees Celsius is your surrounding. 70 degrees Celsius is your system. If you have a heat transfer process in the opposite direction, this statement is valid, right? That is, heat gained by the system, is equal to what? Heat lost by the surrounding. This also satisfies, right? But the problem is what? Your heat transfer process always happens in the direction of decreasing temperature. That is, high temperature to low temperature only heat transfer will happen. Clear? Is that fine? So this is not correct. Right, this is not correct, but what is the problem? According to first law, this is also correct, no? Right, so that is the problem. That's what we are saying. First law is not giving any restriction to these processes. Clear? I hope you understood that. Right, that is, the first law places no restriction in the direction of a process. Right, first law places no restriction in the direction of a process. Clear? But we need what? So due to this particular reason, we need second law, right? Second law to give an idea about the direction of a process. right, to give an idea about the direction of a process. So as we already told, a process will happen, right? So a process will happen only if it satisfies both first and second law. Clear? I hope that part is clear. Clear? I hope that is understood. Now the important part is, right, if I say, right, अगर मैं बोल रहा हूँ this is satisfying first law, right, if I say this will satisfy first law, that will not ensure that that process will happen. ठीक है, मतलब मैंने अभी बोला ना, this process is correct according to first law of thermodynamics, लेकिन वो process होगा क्या? नहीं है ना, there is no heat transfer from surrounding to system. No, that is not possible, right? Surrounding will give heat to system. That will not happen because it is at 30, this is at 70. But this satisfies the first law, no? Right? So only first law will not give you any idea about the process. Clear? So this is the meaning. So once again, a process will happen only if it satisfies first and second law, right? So a process will happen only if it satisfies first and second law. Now what is the other requirement of second law, right? The other major requirement of second law is you need to find this theoretical limits of certain equipments, right? Certain devices, like we have a heat engine, right? We have a refrigerator, we have heat pump, right? So we have devices like this, and we are interested to find what is the maximum theoretical capacity, right? What is the maximum theoretical capacity of these kind of equipments, right? So for that also we are using your second law of thermodynamics. Clear? So I hope you understood this, right? So this is the most important part, why we require the second law of thermodynamics. Clear? So we require the second law of thermodynamics because the first reason is, right, if it satisfies, right, if a process satisfies first and second law, only then we can say this process will occur, right? So that is the first point. Second point is what? We want to calculate the maximum theoretical capacity of these kind of equipments. Clear? So this is the meaning. So these things are there, right? So second law is also used, right? So you can write if you want, in determining the theoretical limits for the performance of, right? So you can write if you want, second law is also used, right? This as a note you can write, right? The second law is also used in determining the theoretical limits, for the performance of commonly used systems like, heat engine, refrigerator, heat pump, right, etc. Right, already done. So next topic is, we can say, thermal energy reservoir, right? So you will be having this term, right? So in the upcoming session we will be having a lot of use of this particular thermal energy reservoir. So what is the meaning of thermal energy reservoir? It is a system with large value of thermal capacity, right? So it is a system, right? A body with large thermal capacity is called your thermal energy reservoir, right? Now we have two type of thermal energy reservoir. One is source, one is sink, right? One is source, you can write, one is source, and the second one is sink. A reservoir that supplies energy in the form of heat, is known as source, right? A thermal energy reservoir which supplies heat is called as source. The thermal energy reservoir which absorbs heat is called sink, right? So you will have two reservoirs. One is ready to give heat, one is getting heat, one is absorbing heat, right? That we will explain, okay, no problem, right? So source, sink, right? So these are the two things. I hope it is clear on the board, right? Okay, right? Source, sink. Now what exactly is the meaning of a thermal energy reservoir, if you are asking, I can say this room is a large thermal energy reservoir, right? Why? Because, for example, in my room, there are a lot of electronic equipments are there, right? That is, for example, TV is there, computer is there. So whatever heat released from that particular devices is not changing anything in my room, right? So the capacity of the room is same as that before. Right, so it is a large thermal reservoir, right? It is able to receive that much heat, and that is not affecting my temperature of the room, right? So then we will say what it is, a large thermal energy reservoir. Clear? So our atmosphere is another thermal energy reservoir. We can say like that, right? So there are a lot of thermal energy reservoirs are there. So source is the one which supplies heat, and sink is the one which absorbs heat. Clear? So this also I hope you understood. Now, right, so I hope up to this is clear. Now, the conversion of work and heat, that is the most important part, right? The conversion of work and heat. So you can see here, we will always say, with this example, you can always remember this example, whenever you have confusion, right? आपको जब भी confusion होगा work heat पे, ये example हमारा chemical वाला example देख सकते हैं आप, right? So this is a reactor, right? This is our stirrer, right? This is our stirrer. If we rotate the stirrer, right? So if we stir this, right? What we are doing actually, we are giving some work, right? We are giving some work, and this work given is converted easily to what? Heat. Clear? So whatever work we is given, right? Whatever work we are applying, we are supplying, right? So by rotation of this particular thing is converted to heat easily. So the meaning is what? Work can be easily converted to other forms of energy or heat, right? Work can be very easily converted to other forms of energy or heat. So can I do the opposite thing, right? Matlab, if I give heat to the system, will I be able to rotate the stirrer? No. Right, so we cannot have the same effect as before, right? मतलब जो हमने equal work दिया था and we were getting the heat. For example, if I give 100 joule of energy by work, right? So that same 100 joule I can get it as heat, no problem. But if I give 100 joule, I won't be able to get a work of 100 joule. Clear? So this is the problem we have. Heat cannot be easily converted to work. Heat cannot be easily converted to work. This is the only difference you need to understand. Clear? So remember this, right? Remember this. If you rotate this, it will transfer heat. So conversion of work to heat is very, very easy, but conversion of heat to work is difficult. Right, conversion of heat to work is difficult. So to make that difficult part easier, right, to make that difficult part easier, we have special devices called heat engines. So what is the use of heat engine? Obviously, we need to convert this heat to work. Right, so for the conversion of for the smooth conversion of heat to work, we need special devices called heat engine. Clear? So यहाँ तक तो ठीक है. I hope you understood. Right. So the conversion of heat to work requires some special devices. So we will call that special devices what? Our heat engine. So I hope all of you know about heat engine. So its easiest part in our thermodynamics is heat engine. Right. So I hope you remember. How will we draw the heat engine? It's very simple to draw the block diagram of a heat engine. That is, this is your heat engine. Right, so what we require for GATE chemical engineering is this much. That is our block diagram. That is, we have a high temperature source. This is our TH. Clear? It is a high temperature source and I am taking heat from this high temperature source. So QH is the amount of heat I have taken from the high temperature source. It can be anything. Right, it can be any source. So from a high temperature source, so this is my source, that is my thermal energy reservoir. So from that high temperature source I have taken heat. Now a part of this heat, by using heat engine, I am converted to work output. Clear? So a part of the heat is now converted to work output. Right? Now what is the problem? Right? According to second law of thermodynamics, the basic logic behind second law of thermodynamics is very simple. We cannot fully convert this heat to work. Right? For example, if you take 1000 joule of energy from the source also, you will never be able to give work input equal to 1000 joule. This is never possible. Clear? So this is never possible. Still people are trying to equate this value. That is, they are still trying. Right? So is there any way we are able to convert this fully? No, it's not possible. Clear? So that is our second law simply. Clear? Now, how much maximum we can convert, that is what we are finding by second law of thermodynamics. I hope now you are able to understand it, right? मतलब हमने 1000 joule लिया है high temperature source से, right? So up to what value we can convert it to work, that is what we are interested in. That will be what? Your maximum theoretical limit. ठीक है? तो ये तो सेम ही है ना? गेट एग्जाम में क्या होता है? Right? Total is 100 marks. Right? Out of this 100, getting 100 is nearly impossible. Right? लेकिन हमारा एम क्या होगा? We want to maximize this. Right? We want to get what? 92, 93, 95, 99. Right? 100 is not possible. Okay. Maybe 90 to 100 is also not possible. ठीक है? लेकिन we are interested in what? We are interested in maximizing this marks. At least 85. At least 80 plus. Right? If you get 80 plus minimum, your rank will be below what? 20. AIR 20. Clear? So we are interested in what? Maximizing the work output. We know it is never possible to convert this 1000 joule, right? So that is complete work of 1000 joule is not possible. So we are interested in what? We are interested in getting the maximum theoretical limit. यही मैंने पहले बोला था आपको. That is what is the use of second law of thermodynamics. We want to know the maximum theoretical limits for devices like heat engine, refrigerator, etc. Clear? Now you can see, right? Now you can see some part is converted to output, ठीक है? And the remaining is rejected. Remaining heat is rejected to a low temperature sink. Right? Remaining is rejected to a low temperature sink. Clear? So you can draw this diagram. So what is the characteristics of a heat engine? Right? What are the characteristics of a heat engine? Right? What are the characteristics of a heat engine? So the first characteristic is they receive heat from high temperature source. You can see, I am not writing this example now. They receive heat from high temperature source. Is it okay? Right? They receive heat from high temperature source. They convert a part of that heat to work output. They convert a part of that heat to work output. Clear? So that also clear, right? So now next is what? They reject the remaining heat to the low temperature sink. Right? They reject the remaining heat to the low temperature sink. Clear? I hope that diagram is visible. Yes. Okay. So clear. So this is what? This is your heat engine. Now, if I say QH is 1000 joule, if I am able to get a work output of 700 joule, what will be the efficiency of the heat engine? It will be 70%. है ना? मतलब आप out of 100 you are able to score 70 marks. Your percentage will be what? 70%. Same meaning here gate में. Right? Out of 100 marks, if you are getting 70 marks in gate, your percentage will be what? 70%. Same thing. Out of 1000 joule, you are able to convert 700 joule means what will be the efficiency? 70%. So how will you write the efficiency of a heat engine? Your efficiency of a heat engine is equal to, what will be the efficiency of a heat engine? That is out of this much amount of heat, out of the QH. Matlab we are interested to convert what? This value, that is maximize this value particularly, right? For example, out of this QH we want to extract maximum. So how much you are able to extract, that is work output. So what will be that? Work output divided by QH. Right? So this work output, can I write this work output as what? QH minus QL, because out of 1000, 700 is converted to work. The remaining will be what? 300 joule will be rejected to outside. So QH minus QL will be what? Work output. So can I write this as, right, what will be this? It will be QH minus QL divided by QH. So I can write it as 1 minus QL by QH. This is the equation of efficiency of a heat engine, right? So a thermal heat engine efficiency equation is 1 minus QL by QH. Is it okay? So please write that equation as well. Clear? So what is the meaning of efficiency of a heat engine? I can say fraction of heat input that is converted to work output, right? That is a fraction of heat input, a fraction of heat input that is converted to work output is called the performance of a thermal heat engine, right? Or we will say the efficiency of a heat engine. So efficiency of a heat engine, what is the equation? 1 minus QL by QH, right? And important part, this QL can never be 0. That is, your QL cannot be 0, because if your QL is 0, what is the point, right? If your QL is 0, your efficiency will be 100%. That is never possible, right? That is never possible. So if QL is 0, your efficiency will be 100%. If the efficiency is 100%, kya meaning hai, right? The meaning is out of this 1000 we are able to convert the complete 1000, right? Out of the given 1000 we are able to score 100 out of 100 in gate. That is the meaning, right? Right. So 100% efficiency is never possible in a heat engine or any cyclic devices. Clear? So this is the point, right? So this QL can never be 0. Now what is, right, what is our aim, right? Why are we learning second law of thermodynamics is we need to know, right? हमें पता है 100 तो possible नहीं है, right? लेकिन 80-90 तो possible हो सकता है ना, right? 80-90 तो possible हो सकता है. So what we are interested in is what? We are interested, right, in all our life, our aim will be to maximize this value, right? Let it be in your life as well, right? So if you are in gate preparation as well, our aim is to maximize this value, right? We need to score above 80 or above 85, above 90, right? So in our mind, okay, you will be knowing that, okay, out of 100 may not be possible, but we need to maximize our marks. Same thing. Why are we learning second law of thermodynamics? Because we want to maximize this particular work output, right? So for that, what are the things we need to do? So that we are going to learn. Clear? So up to this is fine. Right, up to this is fine. So this is about what? Your heat engine efficiency. Clear? So now you can say, so due to this, our efficiency of a heat engine, right? Efficiency of a heat engine will be always less than what? 100% or less than 1, right? So since I am not multiplying by 100, I can say it will be always less than 1. When we talk about efficiency, it is always what? Multiply by 100, right? So we can say it will be always less than 100%. Okay? So this is the meaning. Clear? So this is about the second law. Now we all know the statement of first law, right? We all know the statement of first law. So what will be the statement of the second law, right? So this, they may ask this in your interview, so you have to know this two statement. There are two statements are there for the second law, right? One is given by Kelvin Planck, right? So this is your Kelvin Planck statement. Kelvin Planck statement, right? So this is one statement called Kelvin Planck statement, and we have one more statement from Clausius statement. Both are almost, the meaning is simple, same thing, right? Just now we have discussed efficiency cannot be 100%. This is the logic that should be in your head, right? So that is, meaning is simple, right? Efficiency cannot be 100, but they have given it in different words. So you can see here, it is impossible for any device, if you want you can write it, right? It is impossible for any device that operates on a cycle, right, to receive heat from a single reservoir, and produce net amount of work. So if you see, in heat engine you are having what? Two reservoirs, right? In heat engine you are having two reservoirs. This is your source, this is your sink. So heat engine cannot produce a net amount of work, right, cannot produce a work output without the second reservoir. That is, with only one source we can never produce what, right, we can never produce a work output. This is the meaning of what your Kelvin Planck statement. So meaning is what? There should be some heat sink to reject the heat to surroundings. Clear? So you need source as well as sink, right? You need minimum 2 reservoirs, right? You need minimum 2 reservoirs. That is, with single reservoir it is impossible to produce work. Clear? So this is our Kelvin Planck statement. So you can remember it. Now, since the heat engine is done, right, partially we are saying, right, we have now the refrigerator, right? We have now the refrigerator. So normally in cyclic devices you will be having a working fluid. Right, so you will be having a working fluid. So the working fluid in the refrigerator is called your refrigerant. Right, refrigerant. So this will be going from the compressor to evaporator, evaporator to throttling valve, like that. Now, so since everybody was asking, so what is the meaning of cyclic device? Right, so now we will explain a cyclic device. Right, heat engine is also a cyclic device. So your refrigerator is a cyclic device, heat pump is a cyclic device. So you will see a refrigeration cycle, right? Now for gate you may not require the entire refrigeration cycle, right? But in interviews they will be asking you to draw this particular refrigeration cycle. Clear? So for interview point of view, this refrigeration cycle is very much important to you, right? So after this particular class or something, try to draw the refrigeration cycle by yourself and try to explain it. Right, what is happening inside a refrigeration cycle. For gate, for solving problems, you may require only block diagram of a refrigerator. That is very simple. Right, we may not require vapor refrigeration cycle, right? Your refrigeration cycle may not be required, but we have to understand that as well. Clear? So now next is our refrigeration cycle. Clear? So next topic is vapor compression refrigeration cycle. So this is one of the major questions. Sometimes in interviews they will ask you to draw this. So how to draw this? Right, so very simple. You have 4 major processes happening. Right, you have 4 major processes happening. So always make a cycle. Right, always make a cycle. So since it is a cycle, the important part is you can start your explanation from anywhere. Right, you can start your explanation from anywhere because it is cycle, right? Because it is a cycle. Now first of all, what are the terms? Right, what are the terms? So here you have a compressor. Right, here you have a compressor. So obviously if one side is compression, means the second side you will be having what? Expansion. So here expansion, we can say here it is expansion or it is throttling valve. Expansion, or we can say throttling, right? Throttling valve or throttling, right? Expansion or throttling. Now here you will be having an evaporator. So one side if you have evaporator, this side you will have condenser. So complete the diagram, right? So this thing is the most important part, how you are writing it. Clear? So one side you have compressor, second side you will be having expansion or throttling valve, and one side you have evaporator, one side you have condenser. Clear? So complete this diagram. Clear? Right? So this is done. Clear? So I'm starting from here, okay? This side, you can start from anywhere, it is not an issue, right? You can start from anywhere, it is not an issue because it is a cycle, right? So you can explain from wherever you want. So I am starting with here. Here I am saying we have a refrigerant vapor. Refrigerant is the working fluid, right? Working fluid, right? Refrigerant vapor. I am saying my temperature, for example, 125 kilopascal and minus 25 degree Celsius. Right, 125 kilopascal and minus 25 degrees Celsius for an example, right? So you can see here. Now this refrigerant vapor, right? So it is a cool refrigerant vapor, we can see it is entering into the compressor. So what happens actually, right? So we can see here there is a work input is coming in. I will explain it later, okay? Work input is coming. First we will complete the diagram then, right? So you can write that there is a work input coming in, right? 125, this is now changed to, I can say, if it is compressor means the pressure is increased, also your temperature is also increased. Right, let me say it is 60 degrees Celsius for example, because I have already written 125, no problem, temperature is not problem. Now condenser, so this condenser is releasing some heat to outside because it is condensing, right? It is releasing some heat to outside, you can say. Clear? Now, clear up to this is done. Condenser. Now, it is releasing, okay, it is releasing heat to outside. Clear? Now, I'm saying, okay, 800 kilopascal is the pressure. And I'm saying some temperature is decreased since it is condensing. We can say it is same degree, same temperature also, no problem, right? Now, here we are having so this is your cycle now, right? This is our cycle, vapor compression refrigeration cycle. Now we will explain, right? Now we will explain, right? Now we will explain what is happening, okay? So where should we start the explanation? Wherever, right? You want, wherever you want, I can start the explanation. So I'm starting with my refrigerant vapor here. So my refrigerant vapor is entering into my compressor. Okay? Refrigerant vapor is entering into my compressor. So now I'm switching on my, here is my switch, right? Here I'm switching on my refrigerator, fridge. So when I switch on the refrigerator, I'm giving work input to the compressor, right? So if the compressor needs to do some work means what, right? So we have to give some work input, right? We have to give some work input so that some work input is given. And what is happening? This is compressed. Right, this particular refrigerant vapor is compressed. So obviously what will happen? There is an increase in pressure and temperature. So this high pressure temperature, this particular vapor is entering into condenser. When the vapor is entering the condenser, what will happen obviously? Right, so if it is entering into this particular condenser, the condensation will happen. That is what will happen. The heat associated with the vapor will be released outside. Right, heat associated, the energy associated with vapor, right? If you compare a liquid and vapor, which will have more energy? Obviously vapor. That energy associated, the heat energy or the thermal energy associated with the vapor is gone outside. So I may represent it as QH, right? I will represent it as QH, that I will explain later. So it is a heat going out. Now that vapor, right, so whatever vapor, or if it is condensed to liquid, right, so whatever, now that particular refrigerant is entering into what, your expansion or throttling valve, right? So the heat associated with the vapor is somewhat lost now, right? Now that is condensed and whatever refrigerant vapor is entering into what, your expansion valve, right, or throttling. So what is happening in throttling? Throttling is like your capillary tube. I hope you remember, throttling is your capillary tube. So when it enters the capillary tube, what will happen? Both the temperature and pressure will drop, right? Both the temperature and pressure, both will be dropped. Now, when that particular refrigerant liquid is entering into this evaporator, right? When liquid is entering in this evaporator, what will happen? It is a low temperature liquid. So from your freezer or fridge compartment, what will happen? From this, the evaporator will take heat, right? आपके जो फ्रिज में जो भी food material है, जो भी है, right? So whatever things are there in your fridge, so from that freezer you will take heat so that we should be able to evaporate this particular refrigerant liquid. So we are taking heat from your freezer to the evaporator by using this heat. This refrigerant liquid will evaporate. Clear? This refrigerant liquid will evaporate. So what will happen? Again, it is refrigerant vapor. It is going up. Is there any problem? No problem. Clear? I hope this part is clear. Once again, so that refrigerant vapor is going inside the compressor. By giving work input, we are ready to compress it. We are compressing it. Clear? After compressing, it is going to what? Your condenser. right? After compressing, it is going to the condenser. So in condenser, what is happening? In condenser, we are releasing heat to outside. Clear? And we have a condensation process happening, right? We are having a condensation process happening. Now, if you are asking me why I have shown some temperature difference, simple thing here, right? If there is condensation, maybe you can say there will be some difference between what your sensible heat, right, and your latent heat, right? So to denote that, we have just given a temperature difference, that's all, right? So if there is some condensation to happen, for example, if you have a 150 degrees Celsius vapor at 1 atm, if you want this to condense, we should first decrease this temperature to what? 100 degrees Celsius, then only condensation will happen, right? Same logic, right? Now once that condensation is happening, right, your heat associated with the vapor is lost. Now it is moving to throttling valve. Throttling valve is like what? It is your, I hope you understood, right? So this is like your capillary tube. Yesterday I told you, right, throttling. What happens in throttling? When you have high pressure fluid is entering into this capillary tube, obviously what will happen? There will be a pressure drop, right? Huge drop in pressure associated with a huge drop in temperature, right? So that's why we told throttling will be used, throttling or capillary tube will be used in the refrigeration devices. So there is a temperature drop. So this is a low pressure, low temperature refrigerant vapor, right? Sorry, this is in liquid, right? Because here condensation, after here we are having refrigerant liquid. Those who are having confusion, you can see here. So this liquid is evaporated by using heat that is absorbed from the freezer compartment. ठीक है? So food products से जो भी heat absorb किया है, right? So it will take some heat from the evaporator and it will go. Clear? So this is okay. Is this okay? The explanation for your refrigerator. I hope this particular part of explanation is done. If you need it, right? If you need it, forget what we need is only this much, okay? That is, you can see here, this is your refrigerator, okay? This is your refrigerator. This is your freezer compartment. This is outside. Clear? What we require in gate is this much. To the refrigerator, we are giving work input. Clear? To the refrigerator, we are giving work input. From the freezer compartment, refrigerator is taking heat, QL, right? So that is, this is at a lower temperature, TL, and the refrigerator is releasing heat to outside. So outside temperature is more compared to inside temperature. Clear? So I hope you understood the block diagram of refrigerator. I hope you understood the block diagram of refrigerator. You can see TL is the temperature in the freezer. From the freezer you are taking heat, right? With help of work input, refrigerator is releasing heat to outside, to the surrounding. Clear? So this is the basic thing you need to understand. Clear? So after this class, if you want to know more about this vapor refrigeration cycle, there are a lot of books or there are a lot of YouTube video showing you what the animation. Right, a lot of YouTube videos are there, right? Matlab, to show the vapor refrigeration cycle, animation. With animation, they will understand, right? They will make you understand. That also you can follow, right? That is, this year the classes are online here, right? You can study from anywhere, right? It is not like you have to learn from my class only, no, right? So there are a lot of animation classes, animations are available, right? That is, a lot of videos are there, so you can check, right? If you are not able to understand, maybe in animations you may understand it better, lekin what is the ultimate thing? That is, if somebody asks you what is the vapor refrigeration cycle, you should be able to draw this and you should be able to explain them what are the processes. Clear? So this is done. Now we are interested in what? We are interested in the block diagram only. Clear? You can see we are interested only in this particular part, that is your block diagram, right? So I hope it is visible. Yes, right. So we are interested in only this block diagram. That is, for example, if I draw for heat engine, what was the block diagram? I am taking heat from high temperature source, converting into work output and rejecting it to outside. This was for heat engine. Now for refrigerator, what is the change in refrigerator? Refrigerator or fridge. instead of work output you have a work input in refrigerator, right? Now from the low temperature sink, that is your freezer compartment, you are taking heat to refrigerator. मतलब heat after absorbing the heat हम क्या कर रहे हैं, हम बाहर की तरफ we are rejecting the heat to outside, TH. ठीक है, this is our refrigerator, right? This is our refrigerator. So we have the same kind of term like efficiency in our heat engine. In heat engine the performance was evaluated based on what? Efficiency. In refrigerator we have a new term called COP, that is coefficient of performance of a refrigerator. So we will call it as COP. So you can see here what is the COP of a refrigerator. It is the same thing here, right? What is the importance, right? In our heat engine, out of the heat given, how much we are able to provide work. Now here what is the importance? We are getting energy, right? That is when we switch on this power, we are giving some power input, right? That is to do some work, we are giving money to the refrigerator, right? I am giving 100 rupees to the refrigerator so that I need to get my work done. So out of that 100 rupee I have given to him, how much he is able to produce, that is my point. Clear? So this is the meaning. So what was the objective of refrigerator? Your objective of refrigerator is QL, because out of the work input given, right, out of the work input given, how much heat we are able to take from the low temperature sink. मतलब अपने जो freezer compartment से, right, कितना heat हम ले सकता है, right, how much heat we are able to extract, that is our objective, right? What is the objective of refrigerator? Refrigerator का objective ये है, फ्रिज के अंदर जो भी अपना टेम्परेचर है वो मिनिमम रखना है, right? We need to keep the temperature inside the fridge minimum. So how much QL we are taking, that is our objective. Clear? In refrigerator. Now you can see here work input, can I write it as what? QH minus QL. So this is the equation for what? Your COP of refrigerator. Clear? Right? Coefficient of performance of a refrigerator. Now you can ask, why are we representing it by COP? Because COP of a refrigerator can be greater than 1. मतलब अपना जो COP है ना वो greater than 1 हो सकता है, right? It is possible due to that fact, right? In thermodynamics generally when we say efficiency word, the meaning is it will be less than 100, right? So efficiency cannot be greater than 100 is already fixed with what? First law. मतलब फर्स्ट लो से हम सेकेंड लो से ऑलरेडी हमने बोला है कि एफिशिएंसी 100 के ऊपर नहीं जाना चाहिए, 100 भी नहीं आना चाहिए, है ना? सो इफ वी हैव सम एफिशिएंसी टर्म मोर देन 100, राइट, दैट इज नॉट राइट. सो दैट्स व्हाई दे हैव गिवन अ न्यू टर्म COP, राइट? सो दिस COP कैन बी ग्रेटर देन 1. Clear? The meaning is same there. Both cases the meaning is same. I hope you understood. Clear? Now we have another thing called heat pump. This is for refrigerator. We have a heat pump. Now the importance of heat pump क्या है? Like, what is the meaning of heat pump? Right? And before heat pump, let me introduce you air conditioner. Right? Our AC. Right? So refrigerator and AC will have the same COP here. Right? What is the difference between refrigerator and AC? दोनों का difference क्या है? The main difference is what? द कंपार्टमेंट, राइट? हमारे जो रेफ्रिजरेटर के जो फ्रीजर होता है, राइट, द रेफ्रिजरेटर फ्रीजर इज सेम एज दैट ऑफ व्हाट? रूम फॉर AC, राइट? द मोटिव ऑब्जेक्टिव ऑफ AC इज व्हाट? टू कूल दिस पर्टिकुलर रूम. व्हाट इज द ऑब्जेक्टिव ऑफ रेफ्रिजरेटर? कूल द फ्रीजर कंपार्टमेंट. सेम थिंग, राइट? सो AC रेफ्रिजरेटर विल हैव व्हाट? द सेम COP, no problem. But for heat pump, what is the meaning? Heat pump, we require heat pump to keep a particular room at a particular temperature. We don't want to cool it, we want to heat it, right? So refrigerator and heat pump have the same block diagram. Refrigerator and heat pump have the same block diagram, but the objective will be different. मतलब simple here, right? This is a room, okay? This is my room. This is surrounding. during winter what happens, or during summer what happens? We have an AC, so AC will take heat from surrounding, right? Sorry, AC will take heat from the room and it will reject to outside, so that what will happen? Your room will be always at a lower temperature, right? Now in winter, what will the heat pump do? Heat pump will take heat from the surrounding and will heat up the room, right? This happens in winter. Why we are using heat pump during winter? Because we want to heat the particular room, right? Simple meaning. So you have the same, right? You have the same block diagram in case of heat pump, but only the objective will be different. So your COP of heat pump will be equal to what? Heat pump also requires some work input, no problem, same thing, but in heat pump your objective is QH. Why? Because our objective is to heat this particular room, not to cool the freezer, right? For refrigerator our objective was QL, your heat pump your objective is QH, because we want to heat the room, not cool the room. Clear? So work input, you can write the equation, so you will be having what? QH divided by QH minus QL. Is it okay? So complete both block diagrams and complete both COP equations. So from these two equations, right, from these two equations we can have a relation between what? We can have a relation between COP of heat pump is equal to COP of refrigerator plus 1. Compare two equations, you will understand. Okay, so this equation is also very much important for us. So remember, refrigerator and heat pump operates on the same cycle, right? So this cycle is for both refrigerator and heat pump. Okay? Your refrigerator and heat pump have the same cycle, but the objective is different. Heat pump QH is the objective, refrigerator QL is the objective. Clear? So let us do a problem now. Clear? So once this is done, I hope this part is okay. So can we do a problem? Now you can see the board, right? So this is the question you need to solve. So it's a textbook question, not a gate question, right? So tomorrow we will solve a gate question, because this topic I want to explain it with the problem, that's all, right? So gate problem we will do next. This is a textbook problem, okay? So the question I will read: food compartment of a refrigerator is maintained at 4 degrees Celsius. Okay, so you can see this question. Food compartment of a refrigerator is maintained at 4 degrees Celsius by removing heat from it at a rate of 360 kilojoule per minute. That is, we have a heat removal of 360 kilojoule per minute. What is the required power input to the refrigerator? Sorry, the required power input to the refrigerator is given 2 kilowatt. Now calculate the COP of refrigerator. What is the rate of heat rejection for the same? Calculate the rate of heat rejection to the room. Right, you need to find rate of heat rejection to the room, and you need to find the required power input. Sorry, you need to find the COP. So this is the first question. You need to find the COP and you need to find the rate of heat rejection. So first of all, it's a refrigerator question. So if you want, you can draw the block diagram. What is the block diagram of a refrigerator? We are taking heat from the food compartment. We are rejecting heat to the surrounding by using the work input from the outside. Now, what are the things given? Food compartment of a refrigerator. So your refrigerator food compartment is maintained at 4 degrees Celsius, no doubt. ठीक है ना? 4 degrees Celsius पे maintain किया है. Now, by removing it, how we are able to keep at 4 degrees Celsius? मतलब कैसे हम maintain कर सकते हैं 4 degrees Celsius पे? क्योंकि हम लोग 360 किलोजूल पर मिनट, 1 मिनट पे 360 किलोजूल हीट रिमूव कर रहा है. Right, that is the important point of a refrigerator. In 1 minute we are taking 360 kilojoule of heat, right? Due to that we are able to maintain this at 4 degrees Celsius. Simple. Now the required power input to the refrigerator, so work input or power input is given 2 kilowatt. Now, first question, what is the COP? How can you find the COP? Simple. What is the equation for COP? COP of a refrigerator is out of the work input, how much we are able to take it from the freezer. So QL divided by this. What is QL? QL is 360, right? 360 kilojoule per minute. So kilojoule per minute is what? Right? Kilojoule per minute. How can you convert it into watt? Kilowatt. 2 kilowatt is equal to what? Kilojoule per second. Right? So this is the meaning. So convert minute into this. So 360 kilojoule per minute is nothing but 6 kilojoule per second. Is okay? Right? In 1 minute, if you are able to take 360 kilojoule, in 1 second you will be taking what? 6 kilojoules. Is it okay? Divided by 60, right? Now, QL is 6 kilowatt, work input is 2 kilowatt, so your COP is 3. COP of refrigerator is 3. First question is solved. What is the second question? Rate of heat rejection to the room. What is QH? That's the question. Right? What is QH? Simple. What is QH? QH minus QL is work input, that is 2 kilowatt. You know QH, you know QL. QL plus 2 kilowatt will be QH. So find the answer. QH will be equal to QL plus 2 kilowatt. So QL plus 2 kilowatt. Find the answer. What will be the value of QH? So 2 kilowatt means what? 120 kilojoule per minute. So 120 plus this. So it will be 480 kilojoule per minute. Clear? So this will be the answer for this particular problem. I hope this is also done. Clear? Now, right, so once this is done, what are the things left now in this particular chapter? We have one more statement, right, known as Glacier statement, right, and we have a Carnot cycle, right? So you might have studied Carnot cycle a lot of times. What is the importance of Carnot cycle? That we need to study, right? That we need to study. So next class we will be discussing all the things. So this is only the basics. So we will be starting to solve gate problems also in the next class, right? So hopefully we will continue. Clear? So I hope up to this is fine. Right, so regarding the class timing, right, so this is a recorded lecture, okay, this is a recorded lecture. Since the live classes are going on, right, since 2 live classes are going on, right, so currently in live app also classes are going on, and in your YouTube also it is going on. So we cannot keep the timing always same, okay, that is the only thing. So since it is recorded, right, mostly by the, since the lockdown is getting lifted, right, so mostly by next week or next to next week, hopefully we can start the classes as live also, right? So no problem, right? So we'll be able to start it in live app as well, right? So within maybe 2-3 weeks, right? So it will be able to, we will be, hopefully we can do it, right? So up to that, the timing may change a bit, right? So don't worry, right? So it is, and there will be no delay in the class. It will be completed as soon as possible. Clear? So we'll see the next class will be on Monday, right? So hopefully we can see on Monday. That's all. We'll see you on Monday. Okay. Bye bye.